Everyone, and welcome back to Activity 8. This is our last lesson of Activity 8 and the unit. Today we are going to talk about inverses of functions on the third page of our note packet. Now, what are inverses of functions? They are functions that undo each other. So for instance, we've talked about this back when we talked about exponentials and logs. We talk about how those have that inverse nature with each other because they undo each other. Or think about like we have multiplication and division. Those are undoing each other. That's kind of what our inverses do. We have squares versus square roots, right? Those are undoing each other. So quadratics and our square root functions, those are going to undo each other. So before we get started even talking about the inverses themselves, something that we have to be careful of is the domain restrictions that need to happen on the original. Because if our original function does not pass the horizontal line test, the original domain would need to be restricted. Otherwise, our inverse is not going to exist. So what do we mean by that? If we look at this first example here, we have this function, it's a quadratic, and it is not currently passing the horizontal line test. So we would need to restrict this so that it does. So either you are going to restrict it for the x values that are less than or equal to 3, or you would restrict it so that you would use x values greater than or equal to 3. This tends to be the more popular one, is going with the greater side of it, but officially either one would work. Or if we were using slightly different notation, like for instance, you would restrict for x values from negative infinity until you get to 3, close that parenthesis there, those work. Or you might be able to say from 3 to infinity. Again, either way, these are going to be the restrictions necessary for this to exist. Our second example here is same idea. This is also not passing the horizontal line test. So again, we would need to restrict it one of two ways in order to make this actually work. You would either need to restrict it for x values between -4 and 0, because then that would pass the test, or you could say in different notation, x value would be between -4 and 0. Or, right, we could take the other side, which again tends to be the more popular, using this positive. We would say from 0 to 4 could be a restriction, because then this will pass the horizontal line test. Or from 0 to 4, again, that works out. Because if we only look at part of this graph, so if let's say we took this original and we covered up these pieces so that we're only looking at half of it, now it will pass that horizontal line test and we're good to go. All right, so to actually find the inverse then, once we look at that, we again are always going to start by looking at the original function's domain and range and make sure we restrict anything if necessary. And then to actually perform the operation to find it, you're going to switch the x and the y coordinates in the original and then resolve to get y by itself again. So let's look at some of these examples, okay? On the first one, we want to start, before we even get started looking for it, we are going to look at the original function's domain and the original function's range. So you can either use a graphing calculator, or if you don't have a calculator, I highly recommend that you use Desmos is a great tool. And we have this original function of x minus 2 quantity squared and then plus 1. And we see this function here is one of them that is not currently passing the horizontal line test. Okay, womp womp. So what we need to do is we need to restrict this original domain so that it does either pass, because we limit it to the left-hand side or the right-hand side of that parabola. So best way to do that is this time we want all of our x values greater than or equal to, if we can find those, greater than or equal to, which is toolbar out of my way, greater than or equal to 2. And what happens with that is if we restrict that, we now can see that this will in fact pass the horizontal line test. So that restricted domain is going to be part of this. So x values greater than or equal to 2, so that we now have this passing the horizontal line test. Okay, the next part then is looking at the original function's range. So if we look at the range here, all of the y values greater than 1 or equal to it are going to be possible in our function. Well, this is the, again, original function's domain. We now know that the new inverse domain, f of f inverse, right, is going to have the opposite. The domain is now going to be the range of the original. So our x values are going to be greater than or equal to 1. And then the range in our new one is the original function's domain. So y values are going to be greater than or equal to 2. So we flip that around. And we can confirm at the end when we actually look at this. And from there, to actually get the function anywhere we originally had this is our function, right? So what we're going to do instead is switch this out so that the x and the y switch spots, and our goal then is to get y back by itself. So we're going to start by subtracting 1 over from both sides, and once we get that quadratic isolated, we can square root so that this cancels out, and we're left with the square root of x minus 1 equals y minus 2. Last but not least, to get y by itself, we're going to add 2 to the other side. So our final answer for our inverse is going to be the square root of x minus 1 plus 2. Oftentimes we like to put that plus 2 on the front just so we don't accidentally type it underneath our square root. Now, reminder, we can then check this out. So if we take 2 plus the square root of x minus 1, we see that these are going to be reflections over that line, y equals x. So we know that they are, in fact, inverses of one another. And again, if we check out the domain, it's all of the x values greater than or equal to 1. So we see that that's happening here. And our y values are all greater than or equal to 2. So again, without even graphing these, we can see what the new domain and range are going to be. All right, now for our next function, okay, we have this time a cubic root. So again, looking at this, we have a couple different ways. We'll do this one on the graphing calculator, but we have, if we look here, 6 minus our cube root. So go under the math menu, option 4, cube root of 4x, and then that is all being divided by our denominator of 2 this time. And if we graph this one, we see this one does not need to be restricted because it does pass the horizontal line test. And in fact, the domain and the range of this original function are all real numbers for both domain and range, which means for our new function, g inverse of x, right, the domain and range are also going to be all real numbers because when they flip-flop, we should be good to go. Now to actually calculate, again, our inverse, we start anywhere we see an x in the original will now get switched with the y from the original. So this is now an x over here, and then we have 4y underneath our cube root. So to start this off, we're going to multiply both sides by 2 to get rid of that denominator. And then before we deal with this cube root, we need to isolate it as much as possible. So we're going to subtract the 6. So we have 2x minus 6 on the left equals negative cube root 4y. Divide everything by this negative 1, so that cancels out. And we end up with negative 2x plus 6, and then the cube root of 4y. Now to undo a cube root, remember we are going to raise it to that opposite power of 3. So we have negative 2x plus 6 to the third power equals 4y. And then divide everything by 4. This ends up being our value then, for g inverse of x. Let's save a little room. So this is our inverse function, g inverse of x. And again, if we really wanted to look at this and double check, like, okay, does this make sense? Is it truly a reflection over that line y equals x? Well, we would take our function negative 2x plus 6 to the third power, and then all that is divided by 4. And again, if we graph, we see that we have that line y equals x. This should be negative, minus. There we go. And so we have our original function, we have the line it's reflecting over, and we see that cubic also being reflected over it. So we see that they are, in fact, the reflections. All right, now our next example is looking at a log graph. So again, we want to start by graphing that original to make sure that we don't have any restrictions that need to be restricted. So our original function here is 7 minus log base 3 and then x minus 2. And if we look at this one, we can see that it is not going to need to be restricted, right? It's passing the horizontal line test. So the original function has a domain that, notice, our x values are all greater than 2. There's nothing happening if we look at our table below 2. Otherwise, it's an error message. And then our range is all real numbers, though. Range is all real numbers from negative infinity to positive infinity. So what that means is for our new function, h inverse of x, the domain will be all real numbers, and our y values will all need to be greater than 2. So that flip-flops. And we know if we're starting off with this log function, we know that ideally when we rearrange this, because the inverse of a log is an exponential, our graph or our final equation should be an exponential. Okay, now as we start this off, subtract over the 7, and then we are going to end up dividing by this negative 1 that's out front to make sure that we have that isolated. We end up with negative x plus 7 because everything gets divided by the negative 1, and then we have log base 3 y minus 2. Now that our log is isolated, we are allowed to rewrite this in that exponential format. So the base of my log is 3, so is the base of my exponential. 2 the x plus 7 power is going to equal y minus 2. And then last step, add 2 to that. So that we get our final inverse for h inverse is going to be 3 to the negative x plus 7 power plus 2. All right, now on the flip side of that, for number 4 that I'm running out of room for, right? For number 4, if we check out the original function, we have 5 to the x minus 1 power plus 6. And again, on this graph, we are passing the horizontal line test, so we don't need to worry about restricting the domain. And our original domain on this one is going to be all real numbers. However, our range, we're noticing that we're only having y values greater than 6. So we can plug any x value in, but our y values are only greater than 6's. So our new function, j inverse of x, is going to have a domain that needs x values greater than 6 and a range of all real numbers since they flip-flop. And if we draw in those, we have our own room. Okay, over here we have y equals 5 to the x minus 1 plus 6. So we're going to flip-flop x and y. And then from here, we're going to get x back by itself. So subtract over the 6. And this time we have an exponential, so rewriting it as a logarithm is going to be more useful to us. So we have log base 5 x minus 6 equals y minus 1. Add the 1 to both sides. so that we get our final answer here for J inverse. You can either put the 1 on the end or in front. I like it in front. Log base 5 of x minus 6. Or again, it's okay if you put it as log base 5 x minus 6 plus 1. All right, just remember, though, the plus 1 does not go inside parentheses here. All right, there is one last example for you to try. You are looking for the inverse of this final example. And we will definitely be working more with these in class. Congrats on finishing up Unit 1B.